So this is the first in a series of videos that I'm going to be recording on just some metrics around data sets. So I think a common question I hear is, I produce a data set, how do I tell if it's too diverse, not diverse enough? How do I just sort of understand what my data set has in it? And I think it's a really great question. And honestly, a big challenge, and one that I've seen like little bits of tools here and there to sort of help with it. So I'm going to show a couple things that I've used in the past or that I've seen other people have used, and we're going to work from those. So this is a demo of a notebook on feature extraction and reverse image search. It's actually from Gene Kogan and his amazing machine learning for artists guides and tutorials. So I'm not really doing anything unique here. I'm just basically going to walk you through how to use Gene's notebook. So all the credit here goes to Gene, but I'll just sort of show you how this works. So I updated a little bit in this notebook, and I'm going to use a personal data set that I have rather than the Caltech 101, which is what they use in here. So there'll be a little bit of a difference here and there, but not too much of a difference. And if you can actually download his original notebook and work off that. So I ran this once just to make sure it runs, and now I'm going to use one of my own personal notebooks here. So first thing we need to do is we need to download our data set. So I went ahead and just connected to my notebook here. And I have a data set of cat images that I have put in G Drive. So I'm just going to use GDown to download this. And it looks like I need to change my permissions, so let me do this real quick. Cool, so now I should be able to run this. And I can. So the next thing I want to do is I'm just going to unzip that notebook, or sorry, that zip drive, that zip file, zip drive. God, what is it, 1990? So we're just going to do unzip, run that. And now I have a folder here called 256. I'm just going to rename this. Once I know that's done, it is, and just call it 5 cats. So one thing to note is with this technique, you don't need high-res images. So I generally don't recommend uploading high-res stuff. Those require more processing time. So I just ran this through my dataset tools library and converted all these images to 256. And I don't even think it's square. I think it's just going to smush and do some weird things with it, but we'll see what ends up happening when we run this through it. So this is a pretty raw set of data, just to let you know. Next thing, I don't even know if we need to run this. I added it just because I just always run it. I always add it. We are going to use the Keras library, so I'm going to assume we want to use TensorFlow 1, just because I know this notebook's a little old, so let's just run this and make sure it works. Next, we're going to install a couple libraries and bring them into our Python environment here. So we are going to use Keras. If you've never used Keras before, it's just a big sort of framework for machine learning, and I think it works on top of TensorFlow. Although I think they have a PyTorch version now as well, but we're just going to use the TensorFlow version. Next, we're going to skip this cell. So this cell allows you to download the Caltech 101 dataset. Because I'm not going to use that dataset, I've already downloaded my own. I'm going to skip this cell. So feel free to run it if you want to and you want to use that particular dataset, but I'm going to skip it. Next thing we need to do is we're going to load in VGG16. If you're not familiar with VGG16, it is one of the bigger popular large models. There's VGG16, there's VGG19, there's Inception, there's a bunch of versions of Inception. This notebook uses VGG16, and we'll be able to see sort of what the layers look like when we output this. I think it's fine to start here. You can obviously play with it, and if you want to try to use another different pre-trained networks, there are some other ones here as well at this link. So I'm just going to go ahead and run this cell. It's going to download this version, and I think it just downloads the weights directly. Yeah, it doesn't take that long. I don't even know. Actually, let's take a look and see what. Once it's finishing running, I'll take a look and see what GPU I've been assigned here. Hope that ran. It's because I can't spell NVIDIA. So I'm working off of V100. So I believe that Colab Pro just released some V100s, which is really awesome. It's going to run really, really fast. So that's great. Good, we have a good GPU. If you're on a slower GPU, it'll probably be fine. This doesn't take up, because they're pretty small images, doesn't take up a lot of GPU space. It just might be a slower process. So even if you're stuck on like a K80 or something, I think you'll be fine with this. So we can go ahead and run model summary. This is just going to show us all the layers inside the network. So here you'll see, now we're going to use the FC2 layer for a bunch of our predictions, which means there are 96 neurons. So basically we'll see when we run the first layer of feature extraction, like there's going to be 96 different features that we're looking at. I'm again going to skip this. This is just looking at what object categories are inside of the Caltech 101. I don't really care about this. Because one, I'm not using that data set, but two, like categories aren't really what's important about this notebook. So for that, we're going to skip it. So next thing we want to do is we're going to look at how to forward an image to the network. And basically this is just going to say, we're going to do an example of taking a single image and we're going to run it as a forward pass through the network. And it'll give us a guess or a prediction on what class it's in. This will be kind of funny for this particular model because I don't think we're going to get the right classes, but it doesn't matter for, again, for the feature extraction, which is what we're really, really interested in. So we're going to go ahead and run this. This is just going to save a function as well as import some more modules into our Python environment. So next thing we need to do here is we actually want to grab an image from our data set and we want to load it into the setup. So you'll notice here that the load image function, this is going to load the image in into our tensor, and then it's actually going to resize a little bit. I think it resizes it to 224 by 224. So I've got a 256 size here, so it's just going to squish it down a little bit. That's because VGG16 expects images to be in this shape. So if it's not, it'll throw an error, so you have to reshape everything to this. So even if I have rectangular images, it's going to squish it to a square, which is actually kind of fine for this particular process. But if you're really picky, you might want to convert all your images to squares first. Okay, so I want to grab an image from here. There we go. Sometimes when you have a really large folder, it does take a little bit of time to load these images in. So I'm just going to go ahead and copy the path from one of these files. It doesn't really matter which one you grab, just grab one of them. Go ahead and paste it in here, and then we're going to run this cell, and basically it'll spit out what our image is. Cool, so here's a photo of Venus. If you're interested in what is actually happening here in the output, you'll see that this is a shape of 1 by 224 by 224 by 3. The 3 is that it's an RGB image, right? So there's a red, green, and blue channel. If this were a black and white image, it would be 1. We've resized our image to 224 by 224. So this is the height and width. And this 1 is actually the batch number. So TensorFlow and other neural network libraries can do things in batches. And this just says there's one image in this batch. Cool. So now we can run this predictions model. This, again, it just uses some built-in Keras stuff. So we're just going to run a prediction. I am not sure if cats have been shown in VGG16, so I don't even know if it's going to come up with cats. Again, this is just sort of show that you can do this, but it's not clear to me that like this is actually going to help us. So let's go ahead and run it and just sort of see what happens. Okay, so it did predict a tabby of a probability of 1.96, a hamster of 1.112, a wash basin, which I think is probably like this metal thing that it's probably assuming is a wash basin, a tiger cat. I don't even know what is a tiger, like, is that a tiger or is it a tiger cat, and a lynx. So clearly Venus is a pretty good, it can like break some of the class detection here. But again, we're not really going to use this too much. In fact, I previously ran this on one of my floral data sets, and I don't think flowers are a part of VGG16's class predictions, and it gave me some really wild solutions. So again, this doesn't necessarily matter for feature extraction. We'll look at why in a second. So actually, we'll look at it now. So feature extraction. So essentially what feature extraction does is it runs it through this network, and we get the neurons that have been activated inside the model, right? So at the very end of this model, there's a layer of different neurons, and as it gets through this, it's going to take that last layer, and it's going to sort of activate it. So let's say it is a tabby, right? So there are certain neurons in this layer that get activated more strongly, more strongly. Anyway, so that when those layers are more, or when those neurons are more activated, it is what the classifier can kind of guess is like, oh, that's more likely a tabby, or oh, there's say, and then also in the other side, like let's say there is a neuron for something like I don't know, like a telephone, which clearly Venus is not. This will be very low activation levels. And so basically what we're going to do is we're going to run these images all through this feature extractor, and the feature extractor is going to tell us at each of these layer, like at this layer, what this image activates. And the idea here is that in a good data set, like there should be, like most of your images should probably activate the same neurons, right? If you have two, or especially like in this case, I guess what I'm getting at is this is how you might define diversity, right? You could say that if all of your images activated the last layer of this neurons exactly the same, that might be not diverse enough. Or if it activates them like all within the same sort of level, that could be like a sign of a good level of diversity, but not too diverse, right? And this is the assumption here is that maybe you're trying to build something for StyleGAN, where you don't want too diverse of data sets. It's just going to turn it like output soup. Versus something where you don't want them to feel all the exact same, because then you might not really get that good of an output. So this is me kind of making this up, or like just in talking to other folks, like this might be one way to figure out diversity. All that to say, like let's run through this notebook and sort of see what we actually get when we run this. So next we're just going to load in the model, and we're just going to we're just going to output the summary of what the feature extractor is. So again, it's going to spit out the network for VGG16. So again, this should match exactly what we saw before. You'll see there are a number of layers, and the layer that we're going to be looking at in this example is the very last layer. So this will be the 4096 layer. So now we're going to actually, let's come back up here. Let's grab the exact same image, grab the exact same path, and we're going to paste that path in here. And what this is going to do is it's going to plot all of the activations. So again, there's 4,096 neurons in this, and what we're going to see is how each of them are activated as we run this prediction through this. Let's go ahead and run this. So you'll see that whatever this is, maybe this is the 4,000th neuron, this one gets activated very heavily. You'll see a couple others that are spiked here, and then some that are, almost zero. So the idea here is that if I run another CAD image, maybe this one still spikes, but maybe some of these others are raising and lowering a little bit. So now what we're going to actually do is we're actually just going to run this through the entire folder. So we're actually going to copy the path of this folder. This is just an example of one image, but now we want to run this feature extraction on all of these images. So we're going to go ahead and put in that path. There is a max here. If you probably shouldn't go more than 10,000 just because it's going to be pretty slow. I don't actually, there's probably some like maybe 2,000 images in this folder, so I think we're going to be fine. I'm going to go ahead and run this cell. After I believe like it's going to actually like tell us what images we're keeping and what we're not. Basically, it's just going to say if there's anything in there that isn't a JPEG or a PNG, it's going to like sort of skip them. So we're just going to load these into an image array just so that way we can process it in a minute. Okay, so there's more images in there than I expected. There's 4,740 images. So this might take a little bit of time to actually run, but so far it's run really pretty fast for me. So I'm going to go ahead and run this. Again, this is probably where if you're on a K80 or some slower machine, this might take a little bit longer, but the V100 ran, last time it took like 4 seconds to do 4,000 images. So let's go ahead and run this and see how long it takes. Yeah, so this is pretty fast. This is one of the joys of having a V100 accessible to you. Okay, so as it's running, what's going to happen is we're going to now have a features array that is going to contain I guess it's going to contain what, 4,790. Try that again. 4,740 rows essentially, and then there'll be 4096 columns. So each of these is going to be assigned a basically we're going to get the activation for each neuron in this layer for each of these images. So that's a lot of, that's like, what is it? 4740 times 4096. That is a lot of numbers. So what we're going to do is we're actually going to compress that. So we're going to use a thing called PCA. You don't really need to worry about too much about what PCA is, but essentially what PCA does is it can look at all of these activations and it can sort of figure out what the most important feature vectors are. So let's say, I don't know, let's say neuron 100 for every one of these images was 0. Well, that doesn't, like, that's not really helpful to us, right? Because then we could eliminate that as a thing to consider, right? Because it all has the same vector. So we're going to use a mathematical technique called PCA, principal component analysis, and all it's going to do is it's going to help us sort of find what we're going to do here is the most important 300 vectors. Sometimes those get compressed into, like, you take 2 vectors and combine them. There's a bunch of stuff that can go on here. Math people, if you're watching this, you probably just screamed out loud because that is not a good explanation of principal component analysis. But anyway, we're just going to go ahead and run this. So you can run this. Just this is like a thing that already exists inside of scikit-learn. So we're going to go ahead and run this. So now we have a file. I believe actually we now have a thing called PCA, which is another array, and all it has done is it's compressed everything, right? So we could actually, if we want to look at this, I don't know how legible this is going to be inside of Colab, but if we run this, interesting. Can I do print PCA? It might be that it has to be accessed in a different way. Okay, well, whatever. But there is a PCA. Oh, you know what? This is actually the model. And then let's see. Oh, here we go. So this is where we actually do the transformation to make it happen. So now I believe if we could run so, you know, clearly there's clipping that goes on when you output this in Colab, but you could actually look at all of the newly compressed numbers in this PCA features array. All right, so now there's some really nice stuff inside this notebook. So the first thing we're going to do is we're just going to choose an image at random. So that's really interesting. It pulled in an image that is not at all what I expected in my data set. I haven't cleaned up this entire folder yet. So here we have a video game with Venus and Rue, which I believe Rue is a cat that lives with Venus. And we're actually going to try to find the image that is similar to this. So we're going to run another thing, which is like a similar index. So there's a way to, again, we should find the images that have similar feature vectors. So we're going to go ahead and run this. And then this next cell is going to look for the next 5 most similar images. So inside of this, you'll see that you get 1:6. So basically, we're going to skip 0. 0 is always going to be the same image itself. So we're going to look at the next 5 nearest images. And because we shouldn't have a lot of images like this, I think we're going to get some weird stuff. So let's go ahead and run this and see what happens. And then this cell will actually run it and will actually output those images. So here's something really interesting. Again, because, well, I have a couple of reasons for why this is probably existing like this. One is I didn't run any dedupe on this data set. So my guess is that it had some duplicate images in it. Probably, you know, Venus has a lot of posts and someone probably posted them multiple times. It also looks like Hamilton has also played this game. So Hamilton also had an image in its data set. I wouldn't be surprised if Namcat maybe paid our famous kitties to post. And then it found these 2 illustrations, which are also clearly like have been used multiple times. This is very funny because these are images I didn't know were even in this data set because I hadn't really gone through them yet. So this found some very, very weird images. But you'll notice like this one is very, very far away from these other 2 or these other 3, which are pretty similar. So it's possible that, you know, because this is such a weird image, there are not a lot of good images in this data set to match it. So I'll just say this because this is pretty fascinating. I'm actually really excited to look at this right now. So they then bundle this up into 2 new functions. So basically, like now you can do this with any random image and we'll just automatically split them out. So I'm just going to run this cell to save these functions into our environment. And then here we're going to just run, again, this is going to sort of like simplify this whole thing. So it's going to run all of them. It's going to grab a random image and then it's going to display our 5 images. So, and you'll see I previously ran this on my flowers. So we're going to run this on our cat data set. Cool. So this works pretty much as I would expect, right? Here is a photo of Bone Bone, and we found a bunch of similar Bone Bone images. Now, what's interesting is it's not the exact same pose. This one seems to have orange, or so maybe it's pulling in from some of the orange. Actually, some of these other ones do have orange as well. So we can run this again. So here is a Hamilton photo, and here are other photos of Hamilton, right? And they're sort of in the same pose, maybe like the same sort of crop a little bit, but you get enough similarity or enough difference you could sort of see how this works. So we can run this, this is like a very addictive process. You could run this multiple times and see what you get. So here again is a photo of Omar, blanking on their names. You can sort of see how far, other images that it believes are related to this. So this is essentially what you could do if you wanted to build like a Pinterest reverse image lookup kind of thing. You could run something like this. Here's my Pinterest pinned image. Can I find other images that look just like this? This is one way in which you could go about doing that. So this pretty much wraps up what I want to show in this notebook. The last thing I want to do, just to sort of show you, is you can save these feature vectors. So there is in here in the notebook, there's a way to upload a new image and then find the closest image in your data set using all of the PCA space. You're welcome to do that if you want to. I'm mostly interested in what do we have already with our data set. Last thing we should do is we should download this pickle file. So basically we can turn our PCA features into a pickle file. This will be used in another notebook that I'll go over after this. So let's go ahead and run this cell. Oops, I named this incorrectly. So let's do features 5 cats and run that. And at the very end here, we should have, we have our features 5 cats. So I'm going to go ahead and download this. You could save it to Google Drive. You could do anything with it you wanted to. We will use it in our next video. So in this video, I just sort of showed you the basics of like how to run this, this notebook, how to upload your data set, run feature detection and extraction on your data set, and then doing some of those closest images. So in the next video, I'll show you how to actually do what's called t-SNE, which is a way to orient this on a grid. I think in another video, I'll probably actually go through some of these notes. I have an idea that one thing we could try to do is we could actually take all the images in the data set. We could get the maximum distance between them. And I bet it'd be kind of fun to see, like, compared to FFHQ, where maybe the maximum distance, I don't actually know what the distance numbers look like, but let's say the maximum distance for FFHQ is 1. And we know that FFHQ trains fairly well. We could try this on my cat data set, and maybe we find out that if I cleaned it up better, I could get it down to like a maximum distance of like 5. And that would tell me it's a little bit more diverse than FFHQ, which is probably going to always be true. But maybe it's a little bit closer than I would expect other ways. So, again, it's not like this isn't like a foolproof way to figure out diversity, but it is one technique we use. So I think in another video I'll probably record how to do that using some of the tools that are already here. But I thought this was a really nice way just to sort of show you how we can take just a normal network like a large network like VGG16 and be able to do feature extraction and actually apply these. So this is a really amazing notebook from Gene Kogan. I know Gene is restarting his sort of ML foray. It's been a little quiet for a year or two. I know he's restarting it, and he's got some new activities going on in his Slack channel. So if you're interested in joining him and helping him with some of that work, I definitely recommend checking out his Slack. I'll drop that link to it in the video description, but I definitely recommend. Gene has a ton of these guides, and they're all like, you can pretty much convert them to a Colab notebook pretty easily. Some have a little bit hiccups here and there, but I definitely recommend doing it if you haven't before. And I'm personally really excited to see where Gene takes ML4A, because I learned a ton from using these notebooks myself when I got started. So definitely recommend checking out and keeping an eye on what he's up to. I hope you enjoyed this video. I'm going to try to do more of these as a part of this month's sort of dataset push, since Leah and I are teaching a class on datasets. So if there's other things you're interested in, maybe you have new techniques that I haven't heard of, please feel free to drop me a note either in our Slack channel or on YouTube. And with that, I'll see you next time. Thanks.